This week we're going to introduce yet another relationship or principle that you can use in order to derive equations of motion for a special subset of systems. But before I tell you what that relationship is, let's take a moment and review some important concepts. And the first concept we're going to talk about is mechanical work. So if you have a particle, P, and you have a force acting upon that particle, the work done over a very small displacement, so displacement is a change in position, and so we'll call that dr, and again this is an infinitesimally small displacement. We can write that the work, so work is W, a change in work over that small distance is equal to your force times that displacement. And so now let's consider the case where you again have a particle, but you want to calculate the work done over a larger path. So we're applying a force, right? And here's our particle P, and it's going to cause the particle to move along this path, and so this first position is going to be, we'll call it RO, and then this is RF. And so the work, so the total work done by this force over this path here is, and so we'll have work is equal to the integral of force times the displacement, and this goes from RO to RF. Next, we're going to introduce the work energy principle, which effectively falls out of the fact that if we set Fp equal to ma, which comes from Newton's second law, and we can now plug this into our work equation. So again, if we have work is equal to RO F of Fp dr, then we can set this equal to ma dr. And now we can continue to work through this relationship here. So we can set our acceleration equal to the time derivative of velocity. So we get md, change in velocity over change in time, again still times our dr. And then we can actually take this dt on the bottom here, and we can move that over. So here I'm just going to write the numerator of that fraction, and then I'm going to move the denominator over to below our dr term. And what that allows us to do is, if you think about this, the dr, so that's our change in displacement over dt over time, that actually is going to give us a velocity. So we can now write this term here as our velocity. So I'm just going to rearrange it. So now we have m times our velocity, and then we have dv. And so if you now solve this integral here, what that gives you is 1/2 m, and then you have the velocity at our position RF minus the velocity at RO squared. And this formulation should look a bit familiar to you because kinetic energy is equal to 1/2 mv squared, right? And so the work done, so ultimately what this work energy principle says is that the work done is equal by a force is equal to the change in kinetic energy, right? So this is the work energy principle. And we're going to turn back to that principle in just a moment. But first, I want to define, now that we've defined work, I want to define two different types of forces. And those are non-conservative forces and conservative forces. And this distinction between the two is that when you have a non-conservative force, that the work done will depend on the path taken by the particle. When you have conservative forces, the work done by those forces do not depend on path. And so what do I mean by path dependency? So again, imagine we have our particle, and there's its starting position, and there's its end position. So this is our O, this is our F, and we have a force that's applied. So it doesn't matter. So when you have no path dependency, so a conservative force means that the path that the force makes the particle travel on, right? So you could have a force and it can make it travel along any of these 6 paths, but the work done by those forces will all be identical, because the work done only depends on the starting position, so RO, and the end position, RF. It doesn't depend on the path taken. Non-conservative forces do depend on the path. So examples of conservative versus non-conservative. It's easy to start with conservative. Gravitational forces are conservative, and spring forces. Spring force. Non-conservative forces, some examples are so friction, tension, generally when you have a force applied by, say, maybe it's like a human or something like that. Normal forces, etc. Now, when you have a force that is conservative, you can write that force as a gradient, and we use this del sign to indicate gradient. Actually, it's a negative gradient of a potential. And so this V here is a scalar value. And again, this del figure here, this is equal to, so del is equal to the partial derivative with respect to x in A1 plus partial with respect to y A2 plus the partial with respect to z in the A3 direction. And so just some examples, if you have, again, gravity is a conservative force. So for gravity, our V is equal to mgy, right? Y being, say, the height. So our force is equal to, again, if you have the negative del times V, this is the partial of V with respect to x, A1 minus partial with respect to y, A2 minus partial with respect to V, AZ, A3. And this gives you our force, which again, if you plug in this V, you notice that it only has a y term. So this will go to 0. This will go to 0. The partial derivative of V with respect to y is mg. It's a negative sign, and it's in the A2 direction, right? And so this should be familiar. It's our gravitational force. And the other examples when we have a spring force. So there, V is equal to 1/2 kx squared. And so we have our force, again, is equal to the negative gradient of V, which I'll also write out here. Partial of V with respect to x, A1, negative with respect to y, A2, minus V with respect to z, A3. And so again, there's no y or no z terms, so these will go to 0 if you take the derivative of this partial with, or of this potential V with respect to x, you get kx A1, so negative kx A1. Now returning to our definition of force when that force is conservative, we can actually express the work done by a conservative force in the following way. So we have, again, work is equal to the following. So we have Fp times dr. And so we can substitute now this negative gradient of our potential V in for Fp in this equation. So we get negative Vb dr. Then we can expand this out, so we get negative dv dx A1 plus dv dy A2 plus dv dz A3. And then we can take this dr term, we can actually expand that out into its A1, A2, A3 components as well. So this now becomes dx A1 plus dy A2 plus dz A3. And then this ultimately simplifies down into the following. We end up getting negative sign again in front, dv dx of dx plus dv dy of dy plus the v, oops, that's dc of dz, which then again simplifies down ultimately to RO, RF. This is negative dV. And so if you take the integral of this, you end up with the potential RF. Actually, I should make this RO, sorry, because this is a negative sign. So that becomes RO minus our potential at RF. So now let's turn back. Remember we said that the work done by a force is equal to 1/2 times the velocity at RF minus the velocity at RO squared. And so if the only forces that do work are conservative, then we can equate this above relationship. So we can again write 1/2 m v RF minus v at RO squared. We can equate that with the expression that we got for the work done by conservative forces, which was V RO minus V RF. And so let's just simplify things real quick. Let's call KE, so our kinetic energy, 1/2 mv squared, and then our potential energy as V. This means that we can just rewrite this equation as the kinetic energy at RF minus the kinetic energy at RO is equal to the potential energy at RF minus the potential energy, oh, sorry, this is, again, remember that negative sign, so this is at RO, and this is at RF. And then we can swap these negative terms, and what we get is the kinetic energy at RF plus the potential energy at RF is equal to the kinetic energy at RO plus the potential energy at RO. And you'll notice that both of those are right. You have the kinetic and potential, the sum of the kinetic and potential energy at the position RF is equal to the sum of the kinetic and potential energy at RO, which means that this is going to be a constant value. And this relationship, and so I'm just going to write it above up here, kinetic energy plus potential energy equals constant. This is what's referred to as the conservation of mechanical energy. And for systems where the only forces that do work are conservative, we can use this relationship in order to derive equations of motion. Now, that's not to say that you can't have non-conservative forces in your system. It's just that those non-conservative forces can't do work if you want to use this equation here. So in the next video, I will go ahead and show you how you can use this relationship, this conservation of mechanical energy equation, in order to derive equations of motion.